All right, so we're going to look at section 2.3 tonight. It's calculating limits using the limit laws. So last class we looked at limits. We were looking at graphing them, looking at tables. Now we're going to start looking at how to figure them out more algebraically, so we can come up with exact answers instead of having to do them constantly out. So that's what we're going to start looking at. All right, so first set of limit laws. So as long as the limit of f of x as x goes to a and the limit of g of x as x goes to a, those are the limits that we're looking at if we're breaking them apart. If you have two pieces that are added, you can split them apart, find the limits of those two pieces. Okay? If there's subtraction, you can split the subtraction apart, find the limits of each of the pieces. So one of the nice things about those is that means basically any polynomial I can break up and look at each of the pieces of it instead of having to look at the whole thing at one shot. You can pull out any constant. So in essence, if I'm looking at a polynomial and I've split it up, if I have a coefficient in front of the thing, I can pull that out and just not have to worry about that part. Multiplication, you can split up the multiplication. Division, you can split up the division. So basically all the arithmetic operations, I can just split them apart and look at the limits of each of those pieces individually. They're all in your book. You do not need to write every single one of them down at the moment. So, all right, so let's look at a problem first. So actually, I'm going to see if I can get that graph just a little bigger. There we go. Much better graph. All right, so the first one, we're looking at the limit as x goes to negative 2 of f of x plus 5 g of x. So in essence, that means we're looking at the limit of x goes to negative 2 of f of x. And then 5 times the limit as x goes to negative 2 of g of x. So we can split it up and pull that number out. So now if we look at it, f of x is the red one. So as it goes to negative 2, it's going to 1. So that answer would be 1 plus 5 times. And then the g of x is going to be negative 1. So 5 plus negative 5 is negative 4. So that limit right there is just going to be negative 4. So we can look at it in the pieces. Does that make sense? Some blank thinking. So yeah, you can look at that piece individually and then that. Instead of having to look at the whole thing, which we don't have in this situation, we can look at the pieces to find them. Now if we look at the next one, so we have the limit as f of x and g of x. So that be looking at, so it goes to 1. So the limit of f of x as it goes to 1 is 2. And then the limit of g of x as it goes to 1 is what? It does not exist. Because it goes to 2 different points. So since it goes to 2 different points, it does not exist, which means this limit, the full limit, does not exist. And then the last one was the limit as x goes to 2 of f of x divided by g of x. So we're looking at going to 2. So f of x is, let's say, 1.5. and g of x is 0. So in this case, this limit also does not exist because I still can't divide by 0. So the limit of each of the pieces individually works, but the limit of the whole thing does not work. Any questions on those three? We're going to look at some more regular problems in a second. So, all right. So we got two other ones that we can look at. It's just the power law and the root law. And again, it follows the exact same process. So if I've got something raised to a power, I can find the limit of that thing and then raise that to the power. And then the same thing with the root. So I could, if I'm looking at the limit of this, I can find the limit of the inside piece and then do that new answer to the root. It is all, if you have the book, these are all right in the section too. So, and I will post the notes up online too. So, if you can't see it exactly, because unfortunately, I can't make it any bigger because it's the way the screen is.
Okay, if you can move.
Okay. All right. So let's look at these. So now these are just regular problems that we're going to actually be able to go through and look at. So if we look at the first one, let's look at A. So the limit as x goes to 5 of 2x squared minus 3x plus 4. So we can now, tell you right now, we're going to split this all up. You don't have to. All right? Like this problem right here, you could plug in 5 and get the answer. Okay? We're going to split it up just for the practice of splitting this up. All right? So before everyone goes, do we really have to do all that? No, but we're going to anyway. So the first one, I can take out the 2. So then it's the limit as x goes to 5 of, actually, x. And then we can square it. We can pull the square out too. So in essence, I'm literally plugging in 5 to the x. Minus 3 times the limit of x goes to 5 of x. And plus 4, because it's just 4. Now, while this concept sounds stupid for the problems that we're doing right now, when we start looking at differential, when we start looking at integration, one of the strategies that we use is we'll divide the entire problem by the highest exponent, which gets rid of and makes each part an individual fraction, which makes them all fractions, which will go to 0. So that fraction will end up going to 0. So that's why I'll be able to eliminate a bunch of the pieces, and I'll only be left with what's left over when I'm looking at the limits. So while we're looking at this process of being able to find the limits of each piece really does come back into play later on. So this one, so we have 2. The limit of this goes to 5 is 5 squared minus 3 times 5. So we get 25, 50, 54 minus 15 is 39. So the first limit goes to 39. All right, so now this one's going to the limit as it goes to negative 2. So again, we can split up Which one?
But just today, 6, right?
Oh, yeah, today's the 6th, sorry. Yeah. So we can pull out the x and the 3. So in essence, what we're ended up looking at is we're really just finding the limits of the variable. All over 5 minus the, or 3 limit as x goes to -2 of x. So in essence, we're literally just looking at the limit of the variable because we can pull everything else out of it. So we're plugging a -2 to this whole problem. So I have -2 to the 3rd power plus 2 times -2 squared minus 1 over 5 minus 3 times -2. So we've got -8 plus 8 is 0, minus 1 is -1. And then we've got 5 plus 6, which is 11. So it's -1 over 11. We might be doing this later on, but I want to show you this real quick. All right, so if I plugged in infinity to this problem, what's infinity squared?
Infinity.
Right. So if I plug in infinity to this problem, I'm going to get a bunch of infinities, right? So in this problem, what's the highest exponent? 2. So I'm going to take each part, and I'm going to divide it by 2, x squared. Because as long as I do the same thing to the top and bottom of a fraction, I didn't change the fraction, right? Okay. So what's x squared divided by x squared?
1.
Yep. So it's just 3. And then if I have 1x, I'm going to have 4 over x. And then I have minus 1 over x squared. And then I have 5 plus 3 over x squared. So now, what? Nope. Well, yes, now we're actually going to find the limit as x goes to infinity. What happens if the bottom of a fraction gets infinitely large?
It gets infinitely small.
Right, which means it goes to 0. That's infinitely small. So 4 over infinity is basically 0. 1 over x or infinity squared is 0. That goes to 0. So my limit of this fraction, or this problem I just did is,
0.
Nope, 3/5. It's the only things left.
Okay.
Because all the rest of these pieces here, that goes to 0, that goes to 0, and that goes to 0. So they're all gone. All that's left is the 3/5. The reason we can do that is because I can find the limit of each piece with the rules that we're looking at now. Okay? So while the problems we just did a minute ago was kind of a waste to do it with, the reason we can do this is because of those rules. And that you're going to see so many times in Calculus 1 and Calculus 2, It's the number one thing you're going to use because it allows us to get rid of a lot of stuff. So it makes finding limits a lot easier. Yep. Oh, okay.
It's a dumb question.
Yep.
Why do we throw 0 into the equation for x?
We're not actually, for these,
Yeah.
we're not actually throwing 0 in for x. We're throwing infinity in for x, which makes the fraction, because it's all the infinities are all on the bottom, which makes them 0.
Gotcha.
Because as x gets to infinity, the bottom gets infinitely large, which means my fraction gets infinitely small, which means it goes to 0, which in essence crosses them off, so I don't have to worry about them anymore. Which we couldn't do in the original problem because if I plugged in infinity, I have infinity over infinity, which doesn't work. So by getting rid of them and making them fractions, I can get rid of those things, which makes my problem nice. And if you remember from your pre-calc class, nice little review for your pre-calc class. If you were looking at this is in essence finding a horizontal asymptote. If you're doing horizontal asymptotes, if the exponent on the top and the bottom or the degree on the top and the bottom are the same, your leading coefficients are your horizontal asymptote. So in this case, it's like degree on the top and the bottom are the same. My leading coefficient is 3 good. That's the horizontal asymptote. So that's what we're basically finding with this problem. If the degree on the bottom was the biggest, my horizontal asymptote would have been 0. Everything would have canceled out at the top in this situation. I would have been left off with 0. If the degree was on the top was higher, you'd have ended up with infinity. It wouldn't have worked. Everything would have crossed off, but you still would have left with infinity. So there's no horizontal asymptote. It goes off to infinity at that point. All right. So when example 3 we've actually already done, we did it in class the other day. This is the direct substitution property. This is what we talked about last week. Remember, the first thing you want to look at when you're doing limits is, can I just plug the number in? Okay? So can I just plug the number in and get the answer? Or can I simplify the problem in a way that I can just plug the number in and get the answer? All right? So that's what the direct substitution property says. If you can plug it in, you get your answer. There is a couple limitations to that, and one of the big ones is the piecewise function, which we're going to do in a second. So the first, let's look at this one though. X squared minus 1 over x minus 1. If I plugged in 1 to that, what would I get? Yeah, I'm going to get zeros on the top, right? And zeros on the bottom. So 0 over 0, which doesn't work. However, this is the problem that we actually did last week. You can factor this one. So I can take the x squared plus 1, or x squared minus 1, and change it to x minus 1 and x plus 1. And then the bottom was x minus 1. So I can then cross out the two x minus 1s, and I'm left with just x plus 1. And if I plug 1 into that, I get 2. So that's the direct substitution. I was able to simplify the problem down and then plug the number back into it. Okay. When you're looking at, and it's only going to come up in piecewise functions. Okay? Because any function, if you plug a number into it, it's going to come out to be the number that it's going to. All right. Piecewise functions is where you can get those breaks and the discontinuities and those type of things in it. So in this situation, they're looking for the limit as x goes to 1. If I did a direct substitution into this one, if you plugged in 1, the answer would be up. Okay? However, we're looking at the limit as it goes to it, not necessarily exactly where it is. So what I want to look at is this one. What does this value here go to if I'm going to plug in 1? Okay? In that case, it's 2. So this limit is going to 2 because that's what it's going to, not what it is at that exact point. And like I said, the only time that's going to come up is literally when you see piecewise functions. So if you don't see a function that has multiple parts like the piecewise, you don't even have to actually worry about that.
The g of x is going to 2. Right?
Yeah, the limit as x goes to 1 is going to 2. So that's going to 2. Because we're looking at that first part up top. Even though direct substitution says I would use the pi, because I'm plugging into that thing because that's the domain.
Isn't it like no limit because there's just like pi floating?
No, so if we were to graph this, the first one's just a linear line with a hole at 1. And then that hole would show it pi. So if we're coming in from either direction, we're still going to that 2. So that limit still exists at 2. Even though that answer doesn't exist there, it's at somewhere else. Okay? That's why we have to look at the limit as it's going to it, not just directly substituting that one in. All right, let's look at this problem. All right, so we've got 3 plus h squared minus 9 divided by h. So if I look at this one as the limit's going to 0, can I do it? No, because I'm going to get divided by 0. All right.
So now that's limit of 8.
Yep, is going to 0.
And then you do that, and then it's like 3 plus h parentheses squared.
Yeah. So as it's set up right now, I cannot do it. So let's manipulate the problem a little bit and see what happens. Let's do the 3 plus h squared on the top. So 3 plus h squared would be 9 plus 6h plus h squared. And then if I subtract 9 from that, I would have just h squared plus 6h over h. Which then works out to be h plus 6. So my limit as h goes to 0 is 6. So we simplified the problem down. We got rid of the division in the problem, which was causing my issue. And now I can plug in the 0 and get the answer of 6. Okay? No, I won't jump ahead. I won't actually do that. This problem right here with the h is another thing we're going to see quite a bit going forward, because that's actually the limit definition of a derivative uses h because it's based on the slope equation. And the denominator tells you how far things have changed, so the change in x, which we use the designation of h in that one. So you're going to see stuff like this quite a bit when we start looking at the beginning of differentials. All right, take a minute and see if you can simplify this one out. everybody see or do you want the lights on? Huh? You guys can see fine? Okay. Nice try that. Because in essence, what you did is you said that t or x plus 3 squared is x squared plus 5, and you lost the middle term. Well, the denominator is going to go to 0 if you try to do what you're doing right now. So you have to try something else, because we're not going to split it up.
Oh, wait, I know, I think I know what it is.
Same reason I just told him. It's one of the reasons I like this problem, because everybody tries it.
See something here.
Now, because we have to square the top and the bottom. And so that the square root and the bottom is still going to be something crazy. Because you're still going to have the square root in the middle. So you can just square.
Now, take this one up to 2. Would I? No, I can't.
Huh?
No, I want to put back in this note, because that's calculable.
Actually, that's not. Because if you have to have two different terms to get rid of the middle. So if it's t squared minus 9, you'd be able to factor it. But it's t squared plus 9, so you can't factor it. All right, so there were a couple of people that did this, so I just want to make sure you see this and everybody sees it so that you don't make this mistake, because this is a very, very common mistake. I'm just going to use x because I hate writing t's because they look like pluses. This does not equal this. Okay? Because they just squared both of them, or square rooted both of them. Because if that was the case, then x plus 3 squared would equal x squared plus 9, and it does not. It equals x squared plus 6x plus 9. Okay? So that does not equal that. So you cannot just get rid of the square root like that. Very common mistake. Even if you didn't make it right now, odds are you're going to make it at some point because you just don't think. Okay? So just you can't do that. One of the two pet peeves that I have with little mistakes. You'll see the other one later on. So yeah, you can't not do that. All right. One person actually got it. So the way the problem's written, there's no way to get rid of the square root just by just seeing the square root. So if you're the easiest way to get rid of square roots when you have this thing set up like this is to do
like 1/2, like 2 power 1/2.
no. That'll just rewriting it doesn't actually solve the problem. What you want to do is you want to use this conjugate pair. Okay, so what you basically want to do in this situation is we're going to multiply the top and the bottom of this fraction by the square root of t squared plus 9 plus 3.
Oh yeah, you are like the way you typically write it. The reason why it's italicized and calculated is because it looks nearly identical to a plus sign.
Correct. That's why I hate writing t's. When you're typing it, you can make the nice stylized T and everything else. It doesn't look like a plus sign. When you're handwriting it, it doesn't look that nicely. And I've just never really gotten good at writing the stylized T. Then they just look like J's to me, or at least backwards J's. So we're going to multiply by its conjugate pair. What that does, the bottom is just multiplied because there's nothing really changed in the bottom. The top, however, becomes the square root of t squared plus 9 squared minus 9. because the middle two terms are going to cancel out. And then the bottom is just t squared times t squared plus 9 plus 3. So now the squared and the square root cancel each other out. So all that's left on the top is t squared.
How did that work?
So remember, square and square roots cancel each other out. So this square root and that square cancels out.
Oh.
I'm left with 2 squared plus 9 minus 9.
Oh.
So all that's left is the t squared. Oh, I gotta finish writing the bottom. I finished writing the bottom, it just didn't actually put it up there. There we go. Slow internet. So now I'll be able to cancel out the t squared on the top and the bottom. This is where I said pre-calc really comes into play because the better you are at remembering your functions and how they work and how to manipulate them, the better you're going to be at manipulating this stuff. So now I can do the limit of that.
1 over 6, right?
Yep.
Okay.
So it's 1 over the square root of t squared plus 9 plus 3, which ends up being just 1 over 6. So wait. Yeah, 6. Sorry. Square root of 9 is 3. So yeah, you can start to see how the manipulation is really going to come into play and how you do things. And conjugate pairs are not one you do very often. So that's why this is a great example, is because it's not something you see very often, but it does come up quite often when we're looking at this, especially when we start looking at Calc 2 when you're doing trig substitution, those type of things. We're going to see a lot of square roots, and being able to do the manipulation and the conjugate pairs is actually going to be very helpful. So as crazy as it sounds, this problem in essence was a direct substitution problem. We just plugged the number in to get it. You just had to manipulate the problem beforehand to get to the point where you could just plug the number in. All right. So let's look at these two problems. Look at example 7 first.
Oh, that's easy. That's
What is absolute value?
Absolute value is, it's V-shaped. It's like a V-shape.
It is a V-shape.
Because what it is that if it's negative, it's just like the distance. It's like
Okay.
measuring like.
So what's the definition of absolute value?
I think it's like a measurement of distance.
Well, no, you can use the distance formula with it. But what does absolute value mean? Yeah. All right, so how do you evaluate? Okay, let me ask the question differently. How would you evaluate an absolute value? Yeah. Right, so if it's positive, it stays positive, right? And if it's negative, I got to multiply it by a negative to get rid of the sign, correct? Because it's basically got to become positive, right? Okay. So an absolute value is actually a piecewise function. Okay? And you actually have to evaluate it as such. So what this means is that it's negative x when x is less than or equal to 0. Or actually, it's going to be less than 0. And it is x when x is greater than or equal to 0.
That's how we show that like limit of.
Right. So you can't do the limit of an so because we're trying to make things break things down as much as possible. Looking at the absolute value of or the limit of an absolute value doesn't work as well because it has two different things based on where you are. So because the rule changes when we cross the y-axis, you have to have that understanding there. You have two different rules for each of the domains, which is basically a piecewise function. So the reason mathematicians don't write it like this all the time is because we're lazy and we came up with an absolute value symbol so we don't have to do this. So, but when we're looking at doing limits, we kind of have to go back to that mindset of looking at it separately. So now, if we're looking at the limit of this, so if I'm looking at the limit as x goes to 0 of f of x, now we have to actually, because we have two different directions, we have to look at it as the left side and the right side and see if it goes to the same place. So in this case, the limit as x goes to 0 from the right side of f of x. So as I'm coming in from the right side, I'm going to what? So if I'm coming in from the right side, I'm coming in from the positive side, or that's this way, it's going to 0. So it's going to 0. If I look at the other side as x goes to 0 from the negative side of f of x, it's also going to 0, correct?
Yeah, because they're going to the same.
Right. So in this case, my limit of the whole thing is 0. Which totally makes sense, and everybody totally had well before before we just did that. Okay. Now, the reason why we had to do that one is so when we look at example number 8, you understand why. Because this has more than just the absolute value. So we actually have to do the exact same thing. We have to set up the g of x. We're going to set this up as a piecewise function. And remember, anytime you have a piecewise function, crazy things can start to happen. So my first one, I would have so the very first part, I would negative x over x, correct? When x is less than 0, which is what? What's negative x over x? That's just negative 1. So this problem right here is negative 1 always. When x is less than 0, it's always negative 1. If we do the other side, x divided by x, when x is greater than 0, what's x divided by x? That's 1. So this problem is always 1 when it's greater than or equal to 0. Now you can see why, if we just looked at it as an absolute value, you would never have gotten that. By looking at it as the piecewise function, looking at each individual, now we start to see other things happen. So now we're looking for the limit as x goes to 0 of g of x. So again, we have to look at each side. So the limit as x goes to 0 from the right side goes to what? If we're coming in from the positive side, it's going to what? 1. If we're going from the negative side, it's going to negative 1. They don't go to the same thing, therefore the limit of the whole thing does not exist. Because remember, the limit's got to go to the exact same thing from both sides. Otherwise, it does not work. Anytime you're dealing with absolute value, you kind of got to break it up like this. Even if it was the absolute value of 3x plus 5, you would do the same thing. It's like, okay, 3x plus 5 is less than 0. You'd solve it out so you can figure out where the domain it switches, but the same concept has to happen.
Wait, hold on. Why is the values like different?
Because the
Oh.
absolute value of x is negative x, right?
Oh yeah.
So it's negative x over x, which is
negative 1. Okay.
this one. The other side is x over x, which is 1. That was why we had to do that, because otherwise you wouldn't have seen the split. All right. I guess I can make this graph much bigger. All right. So we're going to look at something known as the squeeze theorem. Yeah. So out of all the ones we're talking about, this is probably going to be the most confusing. So stick with it. If I know that we're going to say the limit of f of x as x goes to 0 is less than or equal to the limit of g of x as x, or x goes to 0, whatever value they use. As long as I know that's true, if there's a function in between it, so like if this one's always lower than this one, and this function is less than this one, bigger than this one, I know it's got to be between those two values. Okay? So the squeeze function basically says, as long, if I know that a function is between these two things, I can use that information to determine what the limit of it is.
If there's a function between two functions.
Yes. So basically, like, so, hold on. I'm almost positive the next one's gonna, yeah, well, I'll make one real quick. So, if, let's say sine of x, okay? What's the range of sine of x? What's the lowest sine of x can be? What's the highest sine of x? Huh? -1 to 1, right? Okay. So I know sine of x is always between -1 and 1. So if I have a function that's greater than -1 always, or less than -1, always greater than -1, I know sine's got to be between those two. Okay? So we can use that information to start figuring out some other stuff. It's confusing until we actually do it. All right, so let's look at this one. Get this one. So can I just plug 0 into this problem?
No.
Why?
Because if there is a 1 over x, and if you plug in 0 into the denominator, it's going to be unplugged.
Very. Yeah, so it's not going to work.
And show that also implies that there is a.
Oh yeah, this is going to work. Yeah, this is definitely going to work. We're actually going to use the squeeze theorem to figure this out. All right, so remember what I was talking about with sine. We know that sine of, not s, just it actually is sine of 1 over x. I know it has to be greater than or equal to -1 and less than or equal to 1. Right? Because sine's got to be between those two numbers. True? Okay. Now, I also know that x squared is always greater than 0 or equal to 0. True? Okay. So we're going to do it. If I take this problem up here and I multiply all the sides by x squared, all three pieces, I get negative x squared is less than or equal to x squared sine of 1 over x is less than or equal to x squared. Correct? So I took this and I multiplied it by x squared. Yes? As x goes to 0 of this. So this piece right here, as x goes to 0, that's going to 0, correct? Okay. The middle piece we can't do because we've already said we can't do that part. And that's also going to 0, correct? So that means this right here has to be 0. Because it's got to be between 0 and 0. That's the squeeze theorem. So in essence, what we knew is we knew it had to be between these two numbers. Okay? We knew that. I don't know what it is, but I know it has to be between those two numbers. So we took the x squared that was here, we multiplied it by 5. And then we can do the limit of that to figure out where it's got to be between. It would. All right, so if we look here, this is what the graph looks like. This is x squared sine of x, sine of 1 over x. You can see how it's getting really, really small in the middle. And we know it's literally between those two functions. Because it's taking whatever sine of x is and multiplying it by the x squared, which is basically that. So that's how it's going to do the curves. So yeah, it doesn't necessarily have to be 0. It could technically have been any number, and you're going to see that going forward. A lot of these things. So like, you gotta remember, a lot of the stuff that we're doing now is setting up things that you're going to use later on to do other processes. All right, and the squeeze theorem is another one of those ones that we use going forward to actually figure stuff out that we might not necessarily be able to come up with that answer, but if I know these two answers, I know it's between those two. And one of the things we use it for is to do like summations of numbers or errors and things like that. When we're looking at integration, we use the squeeze theorem for that too. We just know it's going to be between these two values, so I know it's got to be somewhere in the middle of those two. And it might not even be the same number. We'll figure it out when we're looking at some of the other stuff. We'll come up, and actually maybe not even this calc, it might be in calc 2. You come up with values on both sides and say, okay, this one, it's within 100th of these two values. So then the value, if we cut it in half, it's going to be about here. Might not be the exact answer, but it's approximate enough for our margin of error. So again, these are things that keep coming up. So understanding them on a simplistic scale allows you to start to look at them when they get a little more complicated as we go forward.
Realistically, I've seen the squeeze theorem actually applied for predicting stock price.
Mm-hmm.
There's a chance that you can actually predict the breakout direction of prices. A lot of traders use it for leveraging their position in stock prices and option trading.
Very cool. Yeah, that's the thing. It's like a lot of these things, what ends up happening is a mathematician looks at one situation for it, it's like, oh, we're going to use this. And then other people start applying it elsewhere. The mathematician didn't care. Once they come up with the theorem, it works. We know it works. It's there. You can use it to apply to anything at that point. So yeah, I can see it being used there. All right, go ahead. Oh, I thought you said.
No, I was saying it's pretty crazy because you can actually predict like almost 85% accuracy on what direction prices are going to go.
Yeah, until they screw it up. What was the name of the company? It was in Stanford, actually. I can't remember the name of the company. Oh, Long-Term Capital. There's a whole actually show about it. It was on Nova and PBS and stuff. It was called The $1 Trillion Debt. They did that. They were trying to predict options and everything else, and they did it very well, amazingly well. They were making billions and billions of dollars. And then one domino fell. And then another one fell. And then Russia collapsed. And then this fell. And it was like all of a sudden, none of their formulas made any more sense. Because they couldn't account for it. Because basically what they were doing is when they had one thing, they were leveraging it on another side. And they were basically going back. So they're making little bits on every trade. But those little bits, when they're making thousands and millions of trades, adds up. So what ended up happening was they could no longer balance their equation because too many other things started happening. So it's like, I guarantee you a lot of people got screwed when they were starting to do that when COVID hit. When everything started, it's like because none of their formulas would have made sense anymore because the economy was in such chaos at that point. Yeah. So, and what ends up a lot of times now, what the stock market does when there's so much volatility like that, they just shut down. They figured that out after 9/11. They just shut down. It stopped the bleeding, and then they could figure out. So then things got balanced a little bit more, and then they opened back up. So, and I'm pretty sure there's a million other applications of this that we just can't think of right now. So, all right, let's look at a couple more problems. Well, let's do 3, and we'll figure it out from there. All right, so this one. How do you want to find the limit of this one?
Plug it in.
Perfect. Just plug it in. Okay. So I've shown you a bunch of ways. And if this was the beginning of the class today, we did it, we broke it all out. I do not expect you to do it that way. Okay? I'm showing you to make sure you understand the rules and stuff like that. But in the end, I want you to figure out a way to get the answer. This one, it's just a pure direct substitution. Plug it in and we're going to get the answer. So don't make all this crazy stuff to get the answer when it can be very simple. So this one, we're just plugging it in. So I've got 2 times negative 3 to the third plus 6 times negative 3 squared minus 9. And if we were breaking it all out, that's exactly what would show up anyway. So we got 2 to the 20 times 27 plus, negative 27. 6 times 9 minus 9. Negative 54 plus 54 minus 9. So the answer is
9.
negative 9. All right. Try this one.
And a T 7.
86. Yeah.
86. I figure out how to do it. Switched over.
The 89 actually has a lot more capability. The 89 actually can do integration, differentiation, and everything else on there. It'll give you the answer. It can do symbolic manipulation. So it could factor and everything else. Doesn't show you how it did it, but it can do it. So I guarantee you can do that on that calculator. It's just a matter of figuring out what the operation is. So as I said, look at the math menu. I know there's a list of things you can put in there. All right, so this one just comes out to be 18. All right, try this one. All right, so this one, we can't just directly plug it in. We have to manipulate the problem out to plug this one in.
Involve factoring.
So, yep, this one you have to, well, not actually factor. This one involves foiling, technically. So this one becomes the h squared minus 6h plus 9. When we subtract the other 9 from it, it disappears. So this becomes h squared minus 6h over h. So that ends up being h minus 6, which just comes out to be negative 6 when you plug in the limit of 0. When you're, because inevitably somebody's going to have to do this when they do the test. I need you to show me your work when you're doing the test. I don't have a problem with you showing it to me the way that I'm writing. Notice I'm not writing the limit on every single step. Technically, this doesn't equal this. This equals the limit of this. This equals the limit of that, and so forth. So I'm going to understand that the limit's supposed to go in front of them. So you do not have to write the limit in front of every single one. If you want to, that's fine. I don't have a problem with that. But I'm not expecting that. Okay. We got to remember, I spent 20-something years looking at high school students' math papers, so I'm really good at understanding gibberish and having it all over the place. Oh, that's the other thing. If for some reason you go through and do all your work out and you think it's all wrong, don't erase it. just put an X through it and say it's wrong, okay? Because I have found a few people will sit there and go through and do all the work out. It'll be totally correct. They'll make one little mistake. Then they will redo it and it'll be wrong. So if I see the other work there, I know you understood what you were doing. You made a little mistake. I will give you credit for that. If you erase it all, I can't give you credit for it because it's gone. All right? So never erase your work. The other thing you also can do is, for some reason, going through doing work and you literally have no idea how to get to the answer, just write, I'm stuck. This is what I got. That's fine. Again, I will look at your work and figure out where you made your mistake, and I can give you still points for that. All right? So it's in your best interest to show out all your work and do as much as you possibly can when you're doing your tests. All right? That's going to give you the best score possible. Because remember, the goal is to learn and move forward. So yes, it's a test to make sure you understand it, but if you're making mistakes, I want to be able to fix them so you don't keep making them, because it's just going to carry on through everything. So, all right, one more. This is a pre-calc test, this question. You cannot directly substitute, so don't try. It's going to come out to be 0 on the bottom and 0 on the top. So, yeah, it's going to come out to be 0 but 0. You cannot plug this one. I chose it purely as an actual pre-calc test to see if you can remember how to factor.
When you get to like forwards.
This one's not that bad because this one's in the format of the quadratic, so you can still kind of use the same rules. I did that on purpose too. I will tell you, if you get anything higher, anything that you can't just factor by doing quadratic and stuff, my suggestion to you would be to graph it, find one of the intercept points, and factor it out first, and then work your way down from there. So, but yeah, anything else like crazy, graph it and find the intercept points. That'll pull out a lot of the ones that you could possibly use. And then if there's, it just doesn't pull them all the way down to the end, you can use synthetic vision stuff to pull things out.
Oh. Oh yeah, I see that. Well, maybe you should.
Well, that's always possible. You know, that's the point of reviewing and practice.
You want a graph and find the intersect points and like work that in.
You can do it that way. Not plug it in, factor it out. But this one, honestly, is easier to do this way. If you haven't gotten to the bottom and you think you're going to be stuck, just do it this way.
Oh, 2. Wow. Wow, we are doing stuff.
top should have been pretty easy to factor. X minus 2, x minus 2. If you have anything of a higher degree that's in the like quadratic format, so like an x to the fourth and x squared, if it was x to the sixth and x to the third, anything in that realm, you can basically make it the x squared or the quadratic by just doing a simple substitution. So we use u equals x squared. So we have u squared minus 3 minus 4. So I'm taking u and making it x squared. So that x to the fourth becomes u squared. That x squared becomes u. So now I have a simple quadratic, which I can factor. So I get u minus 4 and u minus 1.
Where did it go?
That was why I'm doing this. Because unfortunately, a lot of these things, these are the little tricks and stuff like that, that you really got drilled in pre-calc, or they should have drilled you this in pre-calc, to do well in this. Because these are the things that are going to help you solve these problems out. So.
Okay, no, it's just I can't find like the parentheses to cancel out.
Right, so now we break out, so we got u to the fourth and u minus 1. I then replace that with the x squared. So I have x squared minus 4 and x squared minus 1. Those are both the difference of squares. So x minus 2 and x plus 2, x minus 1 and x plus 1. I factored it totally out. I didn't need to, because all I really needed to factor was the first one to get rid of the x minus 2. By getting rid of that x minus 2, I now made my bottom so I could plug in 0, or plug in 2 to it and get an actual number. The top still ends up being 0, so it ends up being 0 over 12, which is 0. But now I actually can do that step. So I will have a problem next class that I will show you how to actually factor if you can't factor it quickly out using Desmos to factor it out. To show you how to do that step. Just to remind you guys of those, because you will see some polynomials that aren't easily factorable, and that's one way to pull out some of those factors that we might be able to cancel out. So I'll do one of those on Thursday.